So hello friends, welcome back. So in this video we are going to discuss about 5 examples and we are going to solve all the 5 examples using the Lagrange formulation. So let's start. So here you can see that these are the 5 examples that we are going to cover, and in this video what we are going to do is that we are going to mainly concentrate on the first example. So the reason behind doing this is that as this is going to our first example over this Lagrange approach by the help of some example. So in order to understand this concept in a better way, so I will try to go very slow in this video part, and later when you are going to launch the second video, that video will cover all the 4 other examples, and subsequently we are also going to launch an example set 2 in which we are going to cover some more complicated problems and try to solve those problems using the Lagrange approach, and you will see that how easy it is to use this Lagrange approach. So let's start with the first example. So if we look at the image, so this is some rolling disc which is rolling over this flat surface. So this is a flat surface and these are some fixed constraints. So it is fixed by at one end through some spring, and on the other end there is some damper present. So this means that if there is some motion, that motion is finally going to damped out after some time. Now in this case, let's first assume two coordinate system. So this is our x and this is y, I and j. Now this rigid component has some mass. Let's denote that mass by m, and the moment of it has also some moment of inertia. So let's denote that moment of inertia as by I. So now if I am going to apply some external moment over this component, so what's going to happen? It will start vibrating. So if we have to derive the governing equation for this system, so one way is that we can directly go with the moment approach, or we can also use the force balance and come up with the governing equation. In this case, if you are familiar with Newton's method of force and the moment, so maybe at this point you will think that that approach is easy, but that will be easy only for this problem. So in last video what we have discussed is that Lagrange equations are very helpful when we are dealing with the complicated systems in which there are large number of joints. But for initial simple systems, if you are more familiar with Newton's method, so you can go with that approach also. But I will actually I will recommend you to get familiarized with this approach, because when you are actually dealing with the complex problems, industrial level problems, Newton's method will only give you a very not so detailed insight into the problem, and it will be very complicated to handle those things also. And if you are going to use, eventually you are going to use any simulation software, so in those cases the formulation on which all the softwares are based are mainly of the formulation is based upon the Lagrange approach only, or energy methods. They are not based upon the directly based upon the Newton's method. So let's start. So first, there are 4 steps that we need to follow in order to derive the Lagrange derive the governing equation with the help of the Lagrange equation. So let's first revise those steps that are required for this case. First is that we have to select a complete and independent set of coordinate. Second is that we have to identify load in each generalized coordinate system. So whatever the coordinate system that we have selected, we have to identify the loads in that specific generalized coordinate system, not in the x and y. We will see that if we are going to select some other generalized coordinate system, we need to find this loads only in that specific generalized coordinate system. Third is that we have to find the kinetic energy, potential energy, and the dissipation energy. After finding the kinetic energy, potential energy and the dissipation energy, what we have to do, we have to substitute all the energies in the Lagrange equation that we have derived earlier in our previous lectures on Lagrange equation. Now if I have to choose, means if we start following this approach, first we have to, as this block is moving in x direction, at the same time it is also rotating. Now if this block is not sliding, then there is a specific relation that defines your translation, that connects your translation and the rotation motion. So we have covered this thing in our initial lectures, like if I remember it correctly, it's in our 6th lecture of this vibration series. So in that, if you go back to that video, we have derived this VCM is equal to omega. It means the velocity at which CG of this system is moving forward is equal to omega into r. Now omega is our d theta by dt. Now if we are going to write, VCM is dx by dt is equal to d theta by dt into r. So we can also write it as dx is equal to r d theta. Now if we are going to integrate it from some initial position to the final position, xi to xf, dx is equal to theta 1 to theta 2 r d theta, then we are going to get, suppose that initially it is at 0 position, so x initial will be equal to 0, so x final is equal to r theta plus some constant, and initially theta is also equal to 0, so we can directly write it as r theta 2 or r theta final plus constant. Now using that, like at theta is equal to 0, x is equal to 0, initial condition, so we will get the value of the constant equal to 0, and our equation will become, we can simply write it as x is equal to r theta. So from where here we can see that these generalized coordinates are interrelated to each other. Now we have two options, either we can go with this theta as a generalized coordinate system, or we can go by this, we will go by this x as a generalized coordinate system. Now at this point, as I want to introduce and also make you familiarize with some other type of terms, like kinetic energy due to rotation and kinetic energy due to translation. So I am choosing theta as a generalized coordinate system, but I will also encourage you to derive the same governing equation by starting with x as a generalized coordinate system. Now the second thing is that we have to identify load in each generalized coordinate system. So what it means is that we have to find the load in theta direction. Now if we recall like how we come up with these things, so step 1 is done, we have chosen theta as a generalized coordinate system. Step 2, we have to find a generalized load in theta direction. So this is the formula using which you can compute the generalized load in theta direction. So this is summation of 1 FL dot product DRL by dq1, because we have only one generalized coordinate system, that is theta, so I'm writing simply 1. It is for single degree of freedom, 1 mi dot dwl by dqi1. Now here RL represents your position vector of force location, and ML and FL represents the vector representation of force and mass vector, and at the same time your WL represents angular velocity about which moment is applied. Now if we go back to our image and if we try to compare those things, so in this case you can see that your first Q1 becomes theta. ML becomes mt into k cap. Sorry, this is your not mass vector, this is your moment vector. Now mt into k cap. Why this k cap? Because this is an in-plane motion and the moment is always applied about an out of plane direction. So you can represent it as m into t into k cap. Similarly, your omega L become omega into k cap. Now if we try to substitute these things into the equation, our equation becomes, because there is no external force, so the first term will be 0 and the second term will directly give us mt k cap dot d theta dot by d theta k cap. So this is our mt. So the generalized force in theta direction will be m into t, which is a function of time, and this is the a moment also that we have applied over the system. Now we have covered the two steps, like we have decided the generalized coordinate theta, and based upon that theta we have also calculated the load in that specified generalized coordinate system. So this now we need to, what we have to do is that we have to compute the potential energy, kinetic energy and the damping energy, dissipation energy, sorry. So for that, if we look at the system, there is some spring that is connected to some, and there is some damping part. Okay, so this is a schematic representation of the same system, and it is moving in this direction. At the same time it has some rotation also. Now in this system the potential energy will come due to a spring. Now if we recall, the potential energy for a spring is half k x square, because if even though it is rotating and moving in this direction, so what will happen is that this spring will stretch, or if it is vibrating then it will stretch and compress. So we can write half k and x is equal to r theta square. So this will become your half k r square theta square. Now the damping energy is your half c x dot square. So this will become your half cr square theta dot square. Now the third term is kinetic energy. So can you pause for a minute and just think that what are the components of kinetic energy that will be present in this system? Let me give you an hint. This body is translating, at the same time it is also rotating. So there will be two kinetic energy, will be sum of kinetic energy due to translation part and due to rotation. Now if we recall, the kinetic energy due to translation was half m x dot square plus half I theta dot square. Now we can write it as half ml square plus I bracket theta dot square. Now we can you can go back to this any textbook and you can find the value of this I. At this point I am not writing the value. I will simply writing, like, if we are going to substitute the value of I for this disk, we are going to get half 3 by 2 mr square theta dot square. Now what we have to do is that we have to now substitute all the values in the Lagrange equation. Now, if we recall, the Lagrange equation was something like d by d dt by dq dot minus dt by dq plus du by dq plus dr by dq dot is equal to qi. Now, if we are going to substitute all those things, like T is equal to kinetic energy, R is equal to your dissipative energy, and U is equal to potential energy. So, what you are going to get, you can try substituting these values: mr square theta double dot plus cr square theta dot plus kr square theta is equal to mt. Now, if we compare this equation with the general form of this governing equation, which was something like that for this case, I theta double dot for a rotation part, C I equivalent, we can write it as C equivalent theta dot plus K equivalent theta is equal to mt. Now, suppose that if even though in this video my intention was not to go into so much detail, but suppose if someone asks you what is the natural frequency and the damping factor of this system, so the quick answer to that will be that omega in is equal to K equivalent by M equivalent. So for that we can directly write K equivalent is kr square, M equivalent is 3 by 2 mr square. And if someone asks for damping factor, similarly you can write it as C equivalent by Cc, which will be equal to C equivalent by 2 root under K equivalent into M equivalent, or you can write it as I equivalent. In this case it will be not M equivalent, it will be I equivalent, and here it will also be I equivalent. So in this way, when we have some single degree of freedom governing equation, which can be derived using many approaches, but I usually prefer Lagrange approach. So just by looking at this equation, we can give like what is the natural frequency and the damping factor of the system. So that's all for this video. If you like this video, don't forget to subscribe our channel. That will be really helpful for us so that we will keep making good videos. Thank you.